hopefully we'll also, but I'm not so sure we will today, but definitely tomorrow, we'll go and we'll look at Lagrange multipliers, which is a very interesting technique for solving the same problem, but using a thing called, guess what, Lagrange multiplier to do.
ZZ Top does it?
Say again, Tim?
There's a ZZ Top song called Lagrange, and I think it's spelled the same.
Oh, I didn't know that. Right, so our puzzle here is find three positive numbers. This is kind of where I left off last time, whose product is a maximum. So since we know the sum is 60, that tells us that x plus y plus z equals 60. Well got. And that's a constraint. That basically is some combination of the variables that we're interested in that has to equal something or be less than or equal to something in some cases. We're then being asked to find these three numbers whose product is a maximum. And so the function that we're trying to maximize is a three variable, fourth dimensional function, x, y, z. But what I can do here is I can use that constraint to reduce it to a two variable question. So instead of x, y, z, it now becomes, there we go. It now becomes x, y, and instead of z, I replace it by 60, take away x, take away y, which is that guy. And so we now focus on just this guy. And our job is to find the maximum value for it, right? So I'm going to find a critical number because I know that's where they're going to be. And hopefully there's only one or maybe at most two critical numbers to worry about. And that's all I need to do. I don't need to incorporate that because I've already done it here. So what do I get? I get 60y, take away 2xy, and take away a y squared, and that needs to be 0. And if I do the one with y, I get 60x, take away x squared, and then minus 2xy again. So far, so good. Now, if I remember last time, we did a little bit of working on these two equations. So I'm pretty sure we got to that stage. And can you remember we pulled out a y from here and we pulled out an x from here. So let me write down what that looks like. Y, 60 times 2x, take away y is 0. And that's my new equation 1. And I pull out, I believe, an x from this fella, and I get 60. Take away an x, take away 2y, and that's equal to 0. And I'll call that my new equation 2. And we're trying to find values of x and y that make both these expressions 0 at the same time. So I'm going to go for, well, if y equals 0, this will work. Great. And if you plug y equals 0 into here, what do we get? We get x, 60, take away x, take away 0 is equal to 0. And so what we get is that x could be 0 and x could be 60. So that gives me a critical numbers of 0, 0, and what that other one be? 60, 0. Okay. Now, if I do x equals 0, which is here, and I plug it in here, I will get y, 60, take away nothing, take away y equals 0, and I end up getting two combinations here, which generates 0, 0 again, which we already had, and it generates a very similar looking one, 0, 60. And so I have four critical numbers right now. Still get some more to do. I have 60, take away 2x, take away 2y could be 0. And I have 60, take away x, take away 2y could be 0. And this is essentially a system of equations. And I can solve it by two basic methods. I can do what's called the addition method, sometimes called the elimination method. Or I could do the substitution method. They both work. It's 6 of one, half a dozen of the other. How you're going to do it. For no particular reason, I'm going to take this equation and rewrite it like that. So that's equation 2. I'm then going to replace the x with 60 minus 2y in here. So it's 60, take away 2 lots of x, take away a y equals 0. And what do I get? I get 60, take away 120, plus 4y, take away a y equals 0. I get, I get 3y equals minus 60, so I get 3y is 60. I get y is 20. And if y is 20, and I put it back in here, x is 60, take away 40, so x also happens to be 20. And that is the last critical number. So the answer we're looking for the maximum product is going to come from here, 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 or here, right? So let's take each one at turn and see which one works. Right. If you do x is 0 and y is 0, you also have to find out what z is. And you get z from here, right? And it ends up being 60, take away these numbers. So there's the 3 numbers that add up to 60. Would you agree that their product is just nothing? In fact, if I plug in any of the other 4 up here, like 60, 0, and 0, like 0, 0, and 60, right? All those combinations. Every single one of them also gives me a product of 0. On the other hand, I did have one where x was 20 and y was 20. And if you do a little quick calculation, so is z is 20. And the product of those 3 is the maximum that we were looking for. So if you want 3 numbers to add up to 60, check. And to get the biggest product, the combination that you will use is make all 3 of them 20. And if you do that, you get the answer 8,000. Is there a kind of symmetry in that that kind of makes sense, that should be probably the right answer?
Generally, when you write maximum functions, equal length sides, like a square will be your largest size. So that would make sense.
Right. In other words, all 3 variables being equal to each other seems to be the optimum choice for that question. Now, can I get lots of minimum answers? Yeah, isn't there lots of ways of getting 0, but that's not very interesting. You know, it's not the maximum. That's what we were looking for. So that's a puzzle story. And let's look at a different one. The one I want to look at now are the shortest distance between a point and a surface. So let's find one that looks like that. Keep going, keep going, keep going. They tend to be towards the end, these questions. So let's see if I can find the darn things. Come on, how far can you be? No. No. Still not. Still not. Here we go. God, it took a while. So one of these shortest distance to a point, 17 looks like that. So is question 18. So is question 19. The one I just did, this guy here, that's very like question 20. And that's it. So we've got 3 questions which all involve us finding the shortest distance from a point to some surface in 3D space. So a version of question 17 is that we want to know what the shortest distance from this point to the plane x plus y plus z equals 2. So can you imagine this is in 3D and this is the point? If you were trying to find the shortest distance, it would basically be this guy here. And I'll call it D. Agreed? So our job is to find the shortest distance to the plane. And that's a unique answer, isn't it? If you imagine a flat piece of paper and a point in 3D space, isn't there one point closest to that thing? And we're trying to find what that distance would be.
As long as the plane isn't curved.
Well, when I use the word plane, it automatically means it's flat. I will use the word surface if I mean curved. And when it's curved, which is going to be the second one I'm going to do, we'll see how that adapts.
I had a question really quick.
Yes.
On the last one, and also on this one, I thought about this yesterday, but didn't ask, and then I forgot to ask today. You had x plus y plus z equals 60, and in this problem, you have x plus y plus z equals 2. And you solved for z, and so you said that z equals 2, or in this case, it'd be 2 minus x minus y.
Yeah.
Could I solve for x instead? Like, I don't see a reason mathematically why it wouldn't work with whatever variable.
It will, or y.
Okay.
If the expression is ugly, but one of the three variables, either the x, the y, or the z, is nicest, go that one.
Okay.
So not this one, this is pretty standard, but can you imagine this was x plus y cubed plus z to the 5 equals 2?
Yeah, I would definitely choose x.
Then you choose the x, right? So the goal is, in that question there, it really didn't matter. I just chose z because I felt like it. I could have chosen x and y. Now, first thing I'm going to do is find the formula for the distance between that point here, which has coordinates 3, 0, -2, and a general point on the plane called xyz. Now, way back in the day, didn't you do a thing called the distance formula that would tell you how to find the distance between 2 points? And that formula looks like this. The x coordinate take away 3, because of that, squared. And technically the y coordinate take away 0, right, squared. Plus the z coordinate, take away -2 is add 2. Are you comfortable with that? The distance between those 2 points, a point on the surface, x, y, z, and this fixed point. Our job is to find the maximum value of this function. Great. So I'm going to do a little cheat, but it's a helpful cheat. Would you agree that the maximum value of this is the same place, not the same answer, but the same place as the maximum value of this guy? So if I find out the maximum value of this guy is 25, isn't the maximum distance just going to be 5? If the maximum distance is 100, isn't the maximum distance 10? Why do you think we do this to this expression instead of just doing
because it probably makes it a lot easier to find the derivative.
It does, doesn't it? Would you agree? Chain rules inside chain rules and all that. Isn't it just asking for trouble, right? Now, we're going to do a trick we used on the number question. This has 3 variables. We're going to consider this a constraint. And just because I want to, I'm going to pick Z again. Oops.
Wouldn't it be easier if you picked Y because there's nothing being done to Y?
Okay, I'll do Y.
I mean, just you don't have to worry about it being that equation and then another number being, I guess it would all sort out in the end anyway. But
it does. In this case, you probably don't gain a lot, but you do gain maybe a little bit, so it's worth doing. Pick any one of the 3 letters that you like.
X looks like it could be easy too, because it's a negative squared.
Oh, I guess that's true. And you also have that you're gonna have -2. And so if you do Z, you have -2 and +2. So the constants there would cancel out. So maybe Z was the right choice all along.
Too late now. I'm doing Y. But the moral of this story, can't you do X and Z? And if you're lucky, you picked one that reduced your workload. And if you're unlucky, won't you pick one that maybe make your workload a couple of minutes longer? But won't you still get the right answer in all 3 cases? So it's not a biggie, right? So based on my commitment to doing this fella, and by the way, I should put a little stroke through my Z's because they look really like 2s, don't they? So Z should have a little stroke through the middle so I don't screw up. So
I think you probably put the stroke through your 2 because it's 2 minus X minus Z.
Oh, then 2 take away X, take away Z. Shows you I couldn't even tell which of my 2s was my Z, so I should have done it right at the beginning. So we're leaving the x's alone. We're going to replace the y. And then z plus 2 squared. That's good. I know that says d squared, but can I just call it no, f of xy? Just in my brain, it just makes more sense. Right? Just putting a label on it. So we are going
Wouldn't that
to
be f of xz?
You're right. So I wish I'd just picked Z after all. I would have made less mistakes, right? So anyway, we're back to this guy, right? You don't need to write this one down. I'm just writing it down because it's kind of notes and you might wonder what happened to a variable if I don't write this one. So the partial derivative with x. I do not need to FOIL that out. I could and it would work, but I do not need to. Can't I just use chain rules to save me some time? So here goes. If you do the partial derivative of that, you get 2 lots of x minus 3, technically times 1, which doesn't matter. If you do this fella, you'll get 2 lots of 2x, take away z to the power of 1, times -1. Would you agree in this case it does matter? What about z plus 2 squared? Will you get anything meaningful out of that when you differentiate with respect to x? What's the derivative of that with respect to x?
Well, there is no.
Right, it's just
There's a
nothing,
lot
right?
of this goes away.
Right. And I almost forgot, that's a negative. 2x, take away 6, -2 times that is -4, -2 times that gets me plus 2x, and -2 times that gets me plus 2z, and that's equal to 0. And then combine some terms together, I get 4x, I get 2z, I get take away 10, I believe, which is 0. And I'll call that equation 1. So I would cool with equation 1 down to its bare bones. That's what it looks like. And now I'll do a partial derivative with respect to y. That won't get me anything. This guy will get me 2 lots
Partial derivative with respect to z.
Correct. Actually, good, I did the right answer. This one will get you nothing. This one will get you 2. Take away x, take away z, times a -1, it's chain rule. And this guy gets me 2 lots of z plus 2, technically times 1, and the whole thing is 0. So I now have 4, take away 2x, take away 2z, and I forgot my -1, so I'll do it there, plus 2z plus 2 equals 0. So I ended up needing an extra line because I wasn't paying attention. And what do I get? I get 2x, I get 4z, and I get a -2, and that equals 0. And I'll call that equation 2. So we are essentially looking for critical numbers, aren't we here? And so I need to find out when these 2 partial derivatives are 0 at the same time. I'll just write them next to each other. 4x plus 2z minus 10 equals 0. And that was the one I called equation 1. And then I have a 2x plus 4z, take away 2 equals
For
nothing.
equation 2, should it be, there should be no constant? Because the,
Oh, 2 times 2 gets you 4.
Yeah.
Thank you. Well cut. You know I'm careless. I'm thinking 3 lines ahead of myself, which is not a good idea. Okay, I want to solve these guys. Any suggestions how to do it? There's 2 techniques. Which one do you want to use? Addition method or substitution method?
I mean, we could do elimination if we multiplied the bottom one by 2, because then we would have, or -2, excuse me.
Okay, so let's do this. Leave the top one alone and multiply this guy by -2. And the
Minus
elimination.
8z.
Did you all catch that deliberate mistake? Then you add that together, I get this fella, this fella. I then get that guy. And essentially, I get a Z value of negative 5/3. Are we good now? No mistakes this time? Agree on negative 5/3? Okay, I need to find the other two, don't I? Need to find the X and Y coordinates as well. Okay, how do I get the X coordinate next? I know Z. How do I find the X coordinate?
Shove negative 5/3 back into Z.
Yeah.
Yeah,
Put it
one of
back
these
in the front.
guys. Don't really matter, does it, which one? So I'm picking this one. So it's 4 lots of X plus 2 lots of Z. Actually, I probably should have picked the other one, but too late now. I have 4X, take away 10/3, take away 10 equals 0. I have 4X, that's 30, that's 40/3. Oh, it came out nicer than I thought. Are we happy with X being 10/3? Which means that I now have to find Y, don't I? And we did somewhere, no, I can't find it. Didn't we write down what Y was equal to? Here it is up here. 2 take away X, take away Z. So 2 take away an X, take away a Z. And what does that give us? That's 10, that's 5/3. 6/3, I believe that is 1/3. Does that look correct? Okay. So what we have found, this guy here is actually the point on the surface. So this magic point, now that's the shortest distance, happens to be the point with coordinates 10/3, Y 1/3, and Z negative 5/3. Now, if the question had been, find the coordinates of the point on the plane that is closest to 3, 0, negative 2, wouldn't your answer be just to write that down? But the question was, what is the shortest distance? So what have we got left to do?
Is
Add in
Y
the-
just 3? Or am I crazy? A negative 3?
I hope not. Let's check this one here. Are we good with the 2 take away 10/3, add 5/3 first?
Is
is
it
that what-
10/3 plus 5/3, 15/3, and that's 5? Or
But it's negative 10.
oh, sorry, yeah, never mind.
No, it's worth it. You know what I'm like. It's better to check it and find out I'm right than to let it go and find out I was wrong. So back to this. What will we do now to find the missing minimum distance from point to plane?
Plug the numbers we now have into the
Right.
distance formula.
And I'm now going to cheat and go ... Can you plug it in here, here, and here and get some ridiculous square root and you're finished? So that was an example of a puzzle where we needed to find the shortest distance from a point to a plane. And the next one is going to be the shortest distance from a point to a surface. So the surface is Z squared equals X squared plus Y squared. And we want to find out those. And it ends up being in this question, there ends up being 2 answers, and they describe it as the one that's got the smaller Z and the one that's got the bigger Z. So what are you doing, young lady? I'm going to put you in your kitchen. Right. How can that happen? Let me try and think of one. Can you imagine that we've got a surface that looks like an acorn turned upside down, right? I could have a point. Well, that's probably a bad choice actually, because there could be an infinite number of points. Yeah, I could have a point here, and couldn't it be two guys on the surface that are the closest, but in different points? I'm not sure in this shape that makes sense, because there's probably a point here that's closer. So it is possible to get more than one correct answer. So if I wanted to, and I don't have time, wouldn't I put that into Desmos or GeoBra and actually see what it looks like? Now, since it's the point 2, 2, 0, the distance is the square root of x take away 2 squared plus y take away 2 squared plus technically z take away 0 squared. And if I rewrite this guy as x take away 2 squared plus y take away 2 squared plus z squared, can you see which one of the variables x, y, z would be the good candidate for getting rid of and replacing it by the other two? Here is our constraint. I'm pointing at it. Would you agree z squared?
Yeah, because then that's just a nice direct substitution.
Right. And so d is that guy squared plus that guy squared plus replace the z with x's and y's. And we're not going to use him. Aren't we going to use this guy? Because isn't he easier to deal with, just like the last time? And I'm going to call this guy f of xy. And I would find him 0. I would find him 0. And you end up solving and you find out that there's two distinct answers. I believe one of them's like 1, 1, 2, and the other's like 1, 1, negative 2. So the x's and y's are the same, but the z values are different. Right? Are we cool on that? Because that's as far as I'm going with that. Right? I set the thing up. You're good to go. So we are finished. Any questions, I should say, before I say we're finished? Are we good? Right, let's move on to our last section for this week. I'm going to look at how you using what are called Lagrane multipliers. And we're going to use these to solve max and min problems.
This is the same guy they named the Lagrange points after in space.
I don't know for 100% sure, but I would say it's such an unusual name that the answer is yes. I would think it would have to be. I mean, what's the chances? Right. Very, very clever guy. I believe he's French. He was alive at the time when the French were really good at mathematics. There was like a golden age of French mathematics. Descartes, Lagrange, I can't think of a couple more, but there's at least 3 or 4 like Einsteins of mathematics that were all within about a 60-year period. And he was one of them. Galois, there's another one. So it's strange why that works. If you look at the history of mathematics, there's little bubbles of times when a lot of great mathematicians all seem to appear in one country. and they all kind of feed off each other, I guess, and they kind of cross pollinate their ideas, and that generates even more ideas. And it kind of exploded. And the Germans had an explosion. The Germans did Leibniz, for instance. At his time, there was quite a few really, really good German mathematicians. I mean, that died out. There isn't any decent German mathematicians I know of today, but there isn't any decent Scottish mathematicians right now either, to be honest. Britain did get its time. Taylor series, Maclaurin series, which you're going to, you learn at the end of Calc 3, they were all English stroke Scottish people. They had a golden age. Newton, right, was part of that crowd.
I could have lived without those.
You got what you got. I can't think of a reason why that happens, but it has happened. Right now, there isn't a country that I could talk to and say, oh, Norwegian mathematicians are the cutting edge right now. There just isn't. In fact, if I was going to say anything about modern mathematics, is how much computers have taken over. They actually use computers a lot now because the things that they're trying to solve are so complex you can't do them by hand anymore. Right, so it's all done by computers. Right, back to this fella. We are going to look at how to solve max and min problems using Lagrange multipliers, right? Max min problems. So these are problems that have, and they all should have, constraints. So you'll be given a function, but you'll also be told that x squared plus y squared has to equal 4. That means you can only use points on a circle. Or y equals 2x plus 1. You can only use points on a straight line, or whatever it might be. And there is some really cool videos that you can watch that are very visual, and you can see why this technique works. I'm just going to show you the technique. So I'll jump right in and pick hopefully the simplest question to do that. We have a function, and it's a nice polynomial, that guy. And it has a constraint. The x squared plus y squared has to equal 64. So can you imagine a surface in 3D, and on the ground, they've drawn a circle of radius 8, and only the points in that circle, they meet the surface. So I'll try my best and murder it. It's a very visual thing, which I can certainly imagine, I just can't draw. Can you imagine, whoops, that you've got your circle of points that you're allowed to use in x and y, right? Those guys. And then you've got your surface above it, right? The f of x, y. Your surface, you know, looks like whatever, right? When you take these points up and you find out what they look like, can you imagine that they end up being some kind of peanut-shaped ripple, because don't they follow the value of the surface, right, depending on the shape? And some of them are going to be higher, so it's probably a peanut shape with a slope to it. And you're trying to find the max and the min, right? The maximum z value and the minimum z value of this function using those constraints. So how do we solve it? Well, Lagrange found out that if you find the solution to this problem, so if you find values of x, oops, there should be a y there. If you find values of x and y such that this is true, remember the gradient function we did back? They got a lambda and a g. So let me tell you who g is. See this guy here? Rewrite them like that. So your g is basically what makes your constraint equal 0. And if you solve that, the x's and y's where that is true are the places where the maximum and minimums live. And lambda is a constant, very often called the Lagrange constant, sometimes called the Lagrange multiplier. So that's where the name came from. Well, let's set up the problem. And it's a different kind of algebra, but once you've seen a couple, you'll get used to it. this guy is f of x, comma, f of y. Great. Partial derivative with x, partial derivative of y. This guy is lambda x squared. Oops, I forgot something. G of x, comma, g of y. God, that was close. So the gradient of f will be lambda times the gradient of g. So in this case, I have 2x, negative 2y. I have a lambda, and this guy gets me 2x and 2y. Now I'm going to set these guys up. This fella has to equal this one. So 2x equals 2 times lambda times x, and I'm going to call that equation 1. And negative 2y is going to be 2 times lambda y, and I'm going to call that equation 2. Would you agree that this looks superficially to be impossible because aren't there 3 unknowns, x, y, and lambda, but there's only 2 equations? Shouldn't that be a warning sign that something's not good? You agree? Yet we can solve it. And we're going to do it in a rather sneaky way. Do you notice that these guys here are always going to have lambdas in them because it's lambda times something? If you take equation 1 and you divide it by equation 2, watch what happens. You get 2x over that guy, and you get 2 lambda x over 2 lambda y. Cancel out the 2's, and you get that guy. Cancel out the 2's and lambdas, and you get that guy. And you are looking at xy equals negative xy. So far, so good. Now, does it not become 2xy equals 0? Isn't x equals 0 a possible solution? Would you agree if 2xy is 0, x could be 0? Would you agree that would work? And isn't the other possibility that y has to be 0, right? That's the second one. I guess I'll put them together if that helps. Let's focus on the x equals 0. You then have to say, well, what is the y coordinate that goes along with x equals 0? And this is where you return back to the constraint, because all these points have to be on this circle. So if you tell me x is 0, can't I plug it in here and find out that y could be plus or minus 8? Does that make sense? So when x is 0, y has to be plus or minus 8. So whenever you get an x or a y value, return to the constraint function to figure out who the other guy is. So in this case, x could be 0 or y could be 8. X could be 0 or y could be negative 8. Now, a lot of symmetry going on here. If you do the y equals 0 combination, right, this one here, and you go over here, if y is 0, would you agree x has to be 8 or x has to be negative 8? And so that generates the other 2 guys. We have basically found the 4 possible places for the maximum and minimum value of this function under that constraint, right? The absolute max and min of it. How do I tell which one it is? Well, I go back to the original function now, right, that guy. And I guess I should probably write it like this. And I try out 0, 8, 8, 0, 0, negative 8, and negative 8, 0. So far, so good.
I have a question on where the the 2xy?
Yes. Okay, what's your question? Where it came from or how I used it?
Yeah, where it came from, because I see how you used it, I'm just not sure where.
Okay, right. I took equation 1 and equation 2, and what I essentially did is I took equation 1 and divided the left-hand side and the right-hand side. So if you divide these two and then cancel it down, you get x over negative y. And if you take these two, do you see, basically you get x over y. And from here, I did a little cross multiply. And then I added x, y to both sides.
Oh, okay, that makes sense. Thank you.
Right, right. Normally in algebra, you don't divide one equation with another. Don't you tend to do the addition method or the substitution method? None of those methods really work well with this. We are not finished with this guy because there is a kicker at the tail. Remember, our goal was to find out when these two things, right, worked, right? There is one check that you should always do, and that is check lambda being 0, because lambda is allowed to be 0. Now, if lambda was 0, would you agree that this would be 0? And wouldn't this be 0? Now, wouldn't that become 2x is 0 and minus 2y is 0? And that generates one more possible solution. And so we have indeed got that. So the extra solution, if it exists, and a lot of the time that doesn't exist, or a lot of the time it ends up being one of these, is make lambda 0 and see if there's a solution. And there's a good reason mathematically why we did that. Remember when I divided these two equations? Isn't that okay, provided lambda's not 0? But if lambda is 0 and all bets off, you can't really divide 0 by 0. So we have to check lambda equals 0 as a special case. And I've done that in my head, but are you okay that if lambda was 0, 2x is nothing, so x is 0, and negative 2y is also nothing, so y would be 0. And that's where we got that last guy from. And now we plug this guy in. Nothing squared, take away, that gets you negative 64. That gets you positive 64. This guy gets you negative 64 again. This guy gets you positive 64. And this guy gets you 0. And we are interested in the maximum and minimum, absolute max and min. Would you agree the absolute max is 64? And the absolute mins is negative 64. Now, you could do that by the techniques of yesterday. Can you trust me? It would be really, really ugly math. Did you notice that this lambda equals 0 didn't end up being one of the choices? Very often lambda equals 0 doesn't get you a solution, but the one time that you don't do it is the one time you should have, right? It's that kind of thing where 9 times out of 10, it never gives you an answer that is usable. It's not one of the good ones, but 10, the 10th time it will. Okay, I've done this guy once. Unfortunately, we don't have time today to do it again. So is there any last minute questions on this before we kind of close up for today?
So how do we know whether or not the lambda exists?
How do you know when lambda exists? It always exists. I'm not sure what your question means. Is it, maybe I phrased it and said it doesn't exist. What I'm saying is that it does exist. Lambda equals 0 exists. And when it does, the critical number that you get is in this case, the origin. Can you imagine a different question where we got this thing, right? When we matched them anyway, we got x minus 3 equals lambda x, right? And y plus 1 equals lambda y squared, right? Imagine we did, the stuff and we got that, right? Now, if I made lambda equals 0 here, that's a special case. Won't this guy be 0? So that makes x equals 3. And won't this guy, because 0 times anything is still 0, be -1? Do you see that would generate an extra critical number that you wouldn't have found any other way?
Oh,
No.
okay.
Right. And then what we do is, if that was the situation, wouldn't I do an x minus 3 divided by a y plus 1 is lambda x over lambda y squared? And that way I could remove the lambda and I would just be left with an equation with x's and y's in it. And then I would use that and substitute it into the constraint and hopefully get some solutions out of it. So that would have been the first stage is just check lambda equals 0 in case you will get a critical number, but in case it's one that's useful. And then get rid of it by doing this division technique and cross multiply and so on and so forth, and you are good to go.
Okay, so the lambda just is there to make sure that to check for another critical number.
Yeah, its job is just in case. Because see, if I just did this algebra, I might get 3 or 4 answers. But what I won't get always is this guy. Can you imagine this guy is hidden? And this guy is a special case because doesn't this method not work if lambda is 0? You're not allowed to divide 0x by 0y squared, right? It's just not allowed algebraically. And that's why we treat it as a special case. I don't treat lambda equals 1 or 21 as a special case because this will take care of it. But lambda equals 0, I have to treat as a special case.
Okay.
Okay. Any others? Make sure you say your last name before you go. And you are out of here. And I will see you tomorrow, where we'll get to do lots more Lagrange and multiplier questions.
See you tomorrow.
Okay, see you tomorrow. I'll hang about if there's any more questions.
Have a great day.
You too. Thank you.
I'm glad you knocked me down a peg. I just went to the barber and got my beard trimmed and was thinking I looked really good.
Oh, I'm sorry, Tim.
I don't care. If that was going to hurt my feelings, I'd have a lot bigger problem. Have a great day, though.
Anyway, I only insult people I like, so I like you when I
Worried
insult.
about it.
Right.
All right. Well, have a great day.
You too. Bye-bye.